Hello everyone, very warm good morning to you. We are going to we are going to talk today about a spaceship operator. This topic has been already covered by Hemil in depth in CppIndia Conf. We'll have some overlap, and apart from that, we'll go into a little bit more advanced of spaceship operator. We'll touch upon, we'll see the live examples today, and we'll also touch upon the customization points for a spaceship operator. We'll also see what are the different effect, what are the effect on what is the effect of spaceship operator on the STL. So the goal of this talk is first we'll understand that why we need spaceship operator, what was the problem without a spaceship operators, and how spaceship operator solves that. Then we'll also go through examples, and then we'll see that okay, how does the spaceship operators helps us to write consistent and more readable code. Okay, so the agenda goes like this. We'll first see what is the comparison prior to C++20. Then we'll little bit talk about what is spaceship operator. Then there is something called as rewrite rules. Then there are different comparison categories. Then we'll also touch upon a little bit on default comparison. Then we'll go into the custom comparison. There we'll spend a little bit more time. Then we'll go on overload resolution rules. Then we'll go on to some utilities which is provided by the spaceship operator. Then we'll see STL simplification with spaceship operator. And at the end, if we get a time, we'll see the customization points on the spaceship operator. So let's directly start with a live example. Comparison prior to C++20. Okay, so yep. So if we see, let's say we have a type, some structure type or some class, and I have given some name int type and some given double type name, and it can have some members, functions, and that other things. And I'm not worried about that things. Let's just say that okay, that are there, and as of now we are not worried about that. So what we want to achieve is very simple thing. Let's say there is this int type. We want that int type to be comparable. I mean that we should have this less than, greater than, less than equal to, greater than equal to, equal to, and not equal to, all this defined. On top of that, what we want is this double type is comparable to int type. This is what we want to build. Let's say we are dealing with the C++17. So let me change our standard C++ to C++17. So what we'll basically write, we'll go here and write, it's a bool operator and less than, and then we'll have some const in type ampersand, and let's say const. Okay, and I'm just providing a declaration. We are not worried about, let's say, the implementation as of now. Let's just stick with the declaration, make it very simple. And if you see it here, the first error has gone now. So to remove the other 5 errors, what we have to do, we have to just copy paste this one. Let's say. Okay, and then we just change here the operators. The logic might be different for the different operators. It might be same as well, but yeah, we are a very good program and we know that how to write these comparisons. It is just we are talking about how to declare this variable so that compiler picks up the exact type. Okay, now you see here this is okay. Now if you want to do the comparison with the double type and int type, the option which we have is basically we can write this overloaded operator in one of the int type or double type, or the preferred way is write it as like a free functions. So for example, I am writing this now bool operator once again, and here let's say const data type ampersand, and similarly I'm just writing this guy here as well. Okay, fine, just I'm providing a declaration, no more fancy things. See here, oh sorry, it should be double type. Okay, so double type ampersand and int type. and this error has gone. So similarly, what we need to do is basically once again copy paste the thing, right? And why I'm doing this, because you should realize the pain which is involved doing this thing, right? Because everything is remains same, only the operator is getting changed here, and now everything is passing. So on top of this, for example, now this comparison operator, whatever we have written, if it is let's say, yeah, accessing some private members, then we have to copy paste all these things and declare it as a friend function of double type and friend function of int type, right? So it's a lot of boilerplate code. Even on top of that, let's say, okay, this is done now, looks good, but let's say tomorrow, instead of writing dt1 less than it2, what I just said here, I wrote it2 less than dt2 or dt1, whatever it is, right? And it fails. Why? Because we don't have any less than operator overloaded, where the int type is a first operator and the double type is a second operator. So what we have to do, we have to write all these 6 operations once again, interchange the type. So you see there is a lot of boilerplate code involved here, and it is too much verbose to get very minimal functionality from C++. What is the minimal functionality you want to achieve? The comparison between these two types. Okay, so this is the era before, like, prior to C++20. Now with C++20, it comes okay, sorry, yeah. So with C++20, the spaceship operator got introduced. So what is a spaceship operator? It is a simple 3-way comparison operator. So what is the form of spaceship operator? It has a form of LHS spaceship operator RHS, because it's a binary operator, and it returns an object such that if LHS is less than RHS, then whatever the object is written, that is comparable to 0 and will be less than 0. See, I am saying it is not integer. I'm not saying that LHS, this spaceship operator, returns integer number. It can return any object such a way that the comparison with 0 is a valid operation, and whatever the value it will return, it is basically, this is a true. If it is greater than, then whatever the value which is written, it is comparable to 0 and is greater than 0. And for equal or equivalent case, it will be equal to 0. So what is the difference between equal and equivalent? We'll see that one. The spaceship operator has a higher precedence than relational and equality operators, and it has a lower precedence than a bitwise shift operator. This precedence was decided just to make sure that there are something called as rewrite rule, that rules doesn't break, and you don't have to put a lot of parentheses around here just to make simple things work. So that's why the precedence is higher than relational operators. Otherwise, earlier it was kind of decided that the precedence will be exactly equal to the relational and equality operators. Okay, so let's see how we can basically implement same thing using a spaceship operator. So what I am doing now is I am commenting this everything. Okay, see, everything is commented now. Everything is commented, and now I will here write auto just operator or normal, and once again let me just copy paste this code so that we don't spend a lot of time here. Okay, and if you see, and this should be 20, and let me include include compare. This is needed for a spaceship operator. Okay, and you see here, okay, should not be a problem. Okay, this is still fine. I mean, till this the error is resolved, kind of. Use a to int type operator constant. Is there any typo?
Do you have to say hyphen default equal to default?
No, we are still,
Okay.
oh, sorry. So because it is atto, it will not be able to correct, right?
Yeah,
So
without a
let's
body,
say
it won't know
STD.
what it is returning.
Yes. So let's say we know it is strong ordering type. We'll cover the strong ordering and other things, right? So you see all these errors are gone now. But the is equal to not equal to errors are not gone yet. So what we need to do is basically once again write our the same operator, right? Is equal to, that's it. And this should work. And now if you see here, I have even haven't declared this not equal to, still it worked. How does it work? We will see it very soon. Now let's talk about this. So this is also very simple. We just basically copy these things and okay, make it a free function. And here it is const in type, and I'm just saying double type here. Now once again, if you see here, the order doesn't matter. Okay, and it can't be const here because it's not a member function. And yeah, this still things works, right? See, everything is compiling now. What we added, just two functions here, two functions. Okay, so this is what the spaceship operator does. It removes all this boilerplate code and make our life very simple. When we'll come to a default comparison operator, then we'll see that okay, we don't even require code on line number 13. We don't even require code on line number 28, and still everything works fine. Okay, so let's go to the next slide. And we'll stop for comparison. Okay, so what is the rewrite rule then? So basically, if you are writing any expression using a spaceship operator, or the spaceship operator is already available and you want to write some relational operator, for example, you want to write a relational operator b, then that expression can be rewritten as a spaceship operator b and whatever the relational operator and comparison with the 0. For example, if you are doing a less than b, then it can be written as a spaceship operator b less than 0, a greater than b, a spaceship operator b greater than 0. You just replace the at the rate with your whatever proper appropriate type of relational operators. This is not true for is equal to and not equal to. We'll see why it is not true. The one advantage with this rewrite rules we get is that it supports a consistent comparison. So what is mean by consistent comparison here is, so basically when you say a less than b, then you can basically write it in another way as well. All right, you can just change the order and still the operator should be defined. And basically in that case, to achieve that, this whatever the relational operators are there, they can be again rewritten in another form, which is called as synthesized form, and where you see basically what we are doing is, sorry, there is a typo here. It's not a spaceship operator b, it should be b spaceship operator a in the third column. Everything it should be b spaceship operator a, b spaceship operator e. So here what we have changed, we have just changed the order, and if you have changed the order, then we have basically have to change the comparison as well. So earlier we were, let's say for less than 0 we were checking, now the value will get changed and we have to check greater than 0. Okay, so this is how it supports a consistent comparison. So that's why when you saw that even if I change now the order of less than or greater than, it doesn't matter, still it will be able to find out the correct set of operators and do the comparison. Now let's talk about these equality operators. So the earlier proposal was somewhat like, deduce the equality operators again using this spaceship operator. But there was a problem with the performance. For example, if you want to just compare, let's say, two arrays which are like a million size arrays, right? So basically, first what we do, we basically don't compare it one by one by one. What we can compare it, we can just compare the size. And if we compare the size and the size doesn't match, then we can just say whether it's equal or not equal. We don't have to decide greater than or less than in that case. But when they introduce a rule for default generating all these operators, spaceship operator, this relational operator by using a spaceship operator, what they did, they basically tried to generate it using a one by one comparison. So for is equal to, what could have happened? It could have just compared that million, let's say, numbers until they are like the same. Let's say, for example, you have 1 million and 1 million plus 1, and that everything is same, and the last element is basically you don't have it here. So you could have taken that many comparison. So to solve that problem, what they said, okay, we are not going to deduce the equality operator by using the spaceship operator, but we will still be able to rewrite that a is equal to b to b is equal to a, or a is not equal to b to not a is equal to b, or not b is equal to a. So this is the a rewrite tool. It has nothing to do actually with the spaceship operator. Even without defining a spaceship operator, if you try this by just defining the is equal to operator, and you just try b is equal to a, or a is equal to b, it still works fine. So any question till this point? Okay. So I'm assuming no questions going forward.
I have a question.
Yeah.
The swap of the using the equal to determine the not equal to, that will apply to existing code also.
Yes. So if you are compiling your code with the C++20, it will.
Okay.
Yeah.
Nice.
Now you saw, right, when I was writing that example, you saw I wrote something like yesterday, strong ordering yesterday, and then what is that strong ordering basically? Let's talk about that one. So basically, if you think about a mathematics, there are kind of different types of orders are there, and these are corresponding to the strong ordering, weak ordering, and partial ordering. So in C++ context, what is the strong ordering? Strong ordering means it doesn't allow incomparable values. What do you mean by that? It means that at least, so let's say you have two value A and B. Then one of the three statement, A less than B, or A is equal to B, or A greater than B will be true. Right, one of the three statements should be true. Right, that means we are saying it is a strong ordering. What is a weak ordering? Again, weak ordering is the same thing. One of the three statements should be true. But here is a small difference between the equal and equivalent. So what is difference between equal and equivalent? Equal means it is exactly the same. It follows the substitutability principle. So for example, you have two values a and b, and you have function, let's say f. So if you say a is equal to b, then in mathematical term, what you can say, f of a is equal to f of b. But if they are equivalent, then you can't say f of a is equal to f of b. So let's say in our programming, what can be equivalent but not equal? For example, when you write a double, right, there is a still way that you can specify -0 and +0. Even though they are kind of equivalent, right, semantically, but they are not equal. For example, let's say we are doing some string comparison, and now what we want to do in a string comparison, we want to do case insensitive string comparison. Now if you see, let's say my name in a capital and my name in a small, and if I do a string comparison which is case insensitive, it will still result into the equivalent. It is, we will not say that it is equal, right? It's still equivalent only. I can't use my capital letter name in place of a small letter name, right? Other things might not work there. So here what we say, that the values are distinguishable, the equal values are distinguishable. When we say equal, the values are not distinguishable. One example you can say, for example, you are writing, let's say a map, and the key is your value. Now, even if the values are equivalent, and if they are not equal, all right, we might not want to use, let's say, they act as a key. We want to keep them as a different locations, right, due to our constraints. So at such point of time, we can write STD weak ordering. And then there is a STD partial ordering. So what is basically partial ordering? Partial ordering also allows unordered or uncomparable elements. So they have given very good example in let's say the C++ standard. What they say, like you are comparing the family tree. So if you are comparing two person in the family tree, what can happen? You are comparing this less than or greater than. So if you are parent of if whatever the A and B are in your tree somewhere, you can compare. But if it's not in a tree, then you just can't compare that. They are not relatable. So then in that case, if you want to denote such a thing that okay, these are not comparable, then this is unordered. If I have to think from the numbering point of view, let's say there is a nan, right? Not a number thing. Not a number is not comparable with anything. We can't say that okay, not a number is less than 0, greater than 0, or whatever it is the state. It is uncomparable. So when you get such a value, then how will you denote then in C++ context this? Okay, this is not comparable. I can't say this is equal. I mean, I don't have any answer for that one. Less, equivalent, or greater. So in that case, your return type should be std partial ordering, and if you get such type of data type which is uncomparable, then you return std unordered. Okay, so this return type we need to understand a little bit when you want to write our own custom spaceship operators. Okay, let's understand the implicit conversion between them. So the strong ordering is the strongest type. So when you have strongest type, it can't be it can be implicitly converted to weak order or partial order, but it can't be implicitly converted from weak order or partial order. So in this diagram, you see a strong ordering here. It can be implicitly converted to weak ordering. Yes, it can be implicitly converted to partial ordering. So when I say implicitly converted, that means, see, weak ordering also has three things: less, greater, and equivalent. So if in the strong ordering we get a result less, then okay, it is equal to weak ordering less. If we get a greater, then it is a greater. If we get equal in a strong ordering, then in weak ordering we can say equivalent. All the equal values are always equivalent. In the partial ordering also same thing, right? But you can't convert weak ordering to strong ordering. Why? Because let's say in weak ordering you got equivalent. There is no equal to equivalent in a strong ordering, right? Equal is a stronger as compared to equivalent. So you just can't do that conversion as well. And similarly with the partial ordering, you can't just implicitly convert partial ordering to strong ordering or weak ordering. Okay, and this is very much required. So when you are writing your once again a custom comparison operator, and you specify that okay, my return type should be std strong ordering, and inside the function you are returning like a return, and you are comparing the doubles. Now double is like a partial ordering, because it can have that nan values, it can have -0 +0, so it has to support the partial ordering only. So you can't compare the partial ordering to std strong ordering, and then you will get a compilation error there only, which is good, right? Which is really good. So that's the semantic which this implicit conversion and this ordering data types provides to us. We'll go through once the return value for built-in operators, and then we'll go for some questions and some more code. So for example, if you are comparing two operators or two operands here, and one is a bool and another is not, then the program is ill-formed. It needs to be both bool or both not bool. If one is integral type and another is integral type or unscoped enumeration. You remember what is unscoped enumeration? The C style enum, which can be implicitly converted against to integer, which was a major headache for all this enum comparison, right? So if that is the case, and if you don't have to do a narrowing conversion other than if you have to do narrowing conversion, let's say to compare this other than floating point to integer conversion, then again the program is ill-formed. Otherwise, what we will do, the return type is strong ordering. So in simple word, if it is integral type, then okay, the return type is a strong ordering, because integrals can be, you can always say which integer is less than or greater than or equal to another one. There is a definite answer for that one. For all floating point type, this is a kind of a partial ordering, right? I talked about nan -0 +0. For example, you are having the enumeration type, and both the operands are of type same enumeration. Then the result will be whatever the underlying data type is there. Whatever is the spaceship operator, if you apply the three-way comparison to that underlying data type, and whatever is the result, that will be the result. And now let's talk about object type pointers. Okay. So for example, if you want to compare two object type pointers, then what should be the return type? So if comparison is unspecified, then result is unspecified. So what do you mean by the comparison is unspecified? So you remember, if you remember that if you want to compare two pointers, the two pointers should be pointing to the same memory regions. For example, if you are having two pointers which is pointing to two different array, and if you are doing the comparison according to the C++ standard, it is unspecified. So in that case, we will get an unspecified result. For example, if you are having a two pointers which are pointing to two different, let's say, objects or members of two different objects inside, and you are doing the comparison, in that case also it is unspecified. So in that case also the comparison is unspecified. But if the result is specified, that means the comparison is allowed according to the C++ standard, then it is a once again strong ordering, because it is again governed by the integral rules. So this is what the return value. So if you have to remember, like, in very simple word, it is for all the integral type, you can just consider pointer again a case of an integral type, and then it will be strong ordering. And for floating point, it's a partial ordering. We don't see weak ordering into the built-in data types. Okay. Till this point, any question? So I'm going to the next section here. So see, in the last example, what we wrote is we wrote a declaration for the comparison operator, the spaceship operator. But in most of the cases, whenever we want to do comparison, it is like, okay, there are some members, and we just want to compare that members in a particular order. Might be in most of the cases we can just say, okay, in whatever order it is declared, we just compare that members and generate the result, and we have to write that boilerplate code. So now, what if the compiler can write that boilerplate code for us? It can. What if the compiler can generate the definition of spaceship operator as well? So then, along with the C++, when they introduced the spaceship operator, then came this default comparison where we can default any operator. And when I'm saying any operator, it also involves spaceship operators and other relational operators like less than, greater than, and that other types as well. So how does it work? Let's see. So for all other data type, the return type is bool, and for spaceship operator, it is auto, or it can be any one of this steady, strong ordering, partial ordering, or weak ordering. You have to write it by yourself. So, so what happens with the spaceship operator when it generates the default? When we generate the default things, what it does, it basically lexicographically compares the members. When I say lexicographically, it is in a declaration order. So what it does basically, let's say you have some member, 3, 4 members. On the first declaration, let's say there is some member, let's say value 1. What it will do, it will do the value 1 of the current and the other data type, other objects value 1, the three-way comparison. And if the comparison is not equal to 0, let's say it will return that comparison. So when you will write our own custom operator, we'll see that, okay, how does it looks like? Or let's say if there is if that comparison is equal to 0, then we'll go to next. Till what point we go? Till what point? Till to the last variable in the declaration order, or we let's say in somewhere in the middle only we got not equal to 0. That means we got it is not equal. It's not equal to 0. So till that point, we just go on doing this comparison. And this involves everything. For example, you have some inheritance, then all the base class members also will get compared. In again, you have multiple inheritance. Then again, in the declaration order of the inheritance, the comparison will be done. If you have something like a diamond problem, and in that case, it is unspecified whether the comparison operator for the top base class will get executed more than once or only once. So this is how it works. So in most of the cases, you can just write the spaceship operator as a default. But then what is the use case for having these other operators as a default? Let's say if you want to take address of these operators, In that case, it is good to have a name. Then only we can take address. In that case, you can define other operators as well as the default. And this default comparison for all, or default code for all these other operators will get again generated for the spaceship operator. So unless and until you don't have defaulted spaceship operator, you can't default other operators like less than, greater than. I'm not talking about is equal to, and not equal to. I'm talking about less than, greater than, equal to, that 4 operators. So that is a mandatory condition for that default comparison. So let's see one example with our default comparison, whatever the code we just saw, and then we'll see. So for example, now you see the code was getting compiled here. So what I can do, instead of writing here something std strong ordering, I can just say arrow, and I can also generate the definition itself here. And this is like the definition is generated, and here also you can see the default. And the definition also is generated now for that one. Okay, you can see here the definition. You see here this part of code is generated automatically. Okay. Now you can't basically default this thing, right? Because compiler doesn't know what to do with the int type and double type, because it's 2 different data type. So anyhow, we have to write our own definition for this one, and so we'll see that how to write the definition for that one. One good thing about again defaulting this spaceship operator is, so if you are defaulting a spaceship operator, you don't even have to explicitly say that default is equal to. You can basically again omit that one, and then it works. So now if you see actually our code, I mean, if you see here, this all 6 operations got consolidated into just one single function. Let's say if we wanted to maintain that order, then no expect and all other CV qualifiers and that, then this number could have been greater. But here we could just add 1 or 2 more the spaceship operator overloads, and we are good with that one. Now what I want to show you basically is like, okay, whatever this iteration, you see this on line number 33, and now we are doing this comparison. How this comparison is rewritten. So we'll just quickly have a look into the CPP Insights, that how CPP Insights shows this to us. Let's run it here. So for a time being, what I will do, I will just remove this assert here, so that we get a little bit clean code here, and because we just have statement. So now here, if you see, what it did is, when we are saying IT1 is less than IT2 here, okay, I think the font is visible, right? So here what it is doing, it is invoking the spaceship operator, and then it is comparing with this 0 using the less than. Similarly, if you see less than equal to, so less than equal to cases, once again the spaceship operator, whatever is the result, comparing that result with the 0 with less than or equal to operator. So this is how it is rewritten, not just for this like the same data type, but for other data type as well. For example, here if you see, okay, and if you see here, once again the spaceship operator is invoked for integer type and data type. And now we can see here, our order is matching. Let's see if I reverse the order here, DT1, and let's say IT2 here, whatever it is, okay. And if I just compile it once again, now you see change on line number 43. What it did, see here, the order of comparison changed here. So with the operator less than, earlier this, whatever the operator was there, this was on this side. So it was basically what was doing now here is 0 less than whatever is the result. Earlier what it was doing, whatever is the result is less than 0. So that rewriting of the expression is also done here. If you see for not equal to case, once again we have is equal to, and the not is performed there. If you just compile this code, if you just comment everything, let's say, which is related to spaceship operator, comment everything which is related to spaceship operator, and just have the equal to operator defined. In this case, for example, let me just show quickly that to you. And so we don't have anything related to spaceship operator here. Combating this part as well. And I'm just comparing the equality between these two types. Okay. Let's say something like this. So what I do is I basically write this function here, right? And now if I just compile it, so now the standard is C++20. So still it should compile. Yes, it is compiling. Now I change standard to C++17 and I compile it. See, now it failed. So I think this answers your question, Ankur, right? Because in C++17 there was a no is equal to operator where the first argument is double type and the second argument is int type. But the order was like int type first and double type second. But when we enable C++20, right, then it got compiled because it is able to reverse that order and do this comparison. Any question here?
I just have a
Okay.
question.
Yeah.
Can be there a situation when we write a spaceship operator equal to default and there is error, maybe some values that can't be comparable, like any socket or any other thing?
Yes, we'll come to that example. I have such example when we are writing our own custom, let's say operator, right? For example, let's see, this is some int type, okay, and this int type is getting derived from some base type, and that base type not is don't have the spaceship operator defined for base type. Now it's like a constructor, right? If you remember the default constructor, how does it works? If your base class has a default constructor, then it will call that default constructor. If your base class doesn't have a default constructor and you want to have a default constructor in your class, it can't be generated. So similarly, if in the base class, let's say the operator or not in base class, let's say in a member, whatever the member we have, if they don't have the spaceship operator defined for them, then it will not be able to generate the definition. So there you will hit an error. So all the members or all the base class members, everywhere where we are doing the comparison, the spaceship operator needs to be basically already defined. Does that answer your question?
Yes.
Okay. So let's go. Now let's talk about custom comparisons. Okay. So till this point, it was kind of just a revision what we had and almost 46 minutes. So we'll try to go a little bit quickly from here. So, so for example, now we have something like this. So this example is taken from once again cppreference.com. I have done some little bit modification there. So let's say I have some base class and then I have a derived class here, and I want to do this comparison as well. I want to insert this into a set where the comparison is required. Now, how to do that? So one thing is basically what we can do. We can do a default comparison, and then everything will work. So let's try adding some default comparisons. So let me first add a default operator here. For example, auto operator. So, and we have const derived ampersand. Let's say const is equal to default. Now what is happening here? This will answer your question. See, no match for operator on const base. We don't have that operator on the base class. So that's why it's not able to generate a default. So that means what I can do is very simply, I can just write something like this. And here I can say, okay, it is base, and now it works. The assertion fails. We will come to the assertion part, but at least it compiles now. Everything is working fine. Correct. Now let's say if I remove this one. Okay, tell me, if I remove this one, will the code compile or not? Runtime error, the assertion will look. Will the compile code or not? If I remove line number 17.
I think it
Anyone?
should work considering C plus 20.
Yes, it works because see, it is in the base class you have this method available and then it is getting inherited here. So that means you have that spaceship operator available. But the catch here is now this spaceship operator, even though it is auto-generated, will only just compare zip. And now here, let's say I have created two data members, two 1 and 2 2, and there you can see the zip for both is A and A. So when it will try to insert into a set, it will say that okay, this both values are same, and it will just insert it like a single element. And that's why we fail on the assertion that okay, the size equal to 2, because these are kind of setting it as equal. But if I add it here, the second, which let me reverse, then in this case also it works, right? It works because now it is comparing the zip first, and then it will compare tax ID, and then it will compare first name, and then it will compare last name, and then it will return the result. So here you can see the zip is same, the tax ID is same, the C, which is nothing but the first name, which is different, and the last name is different. So as it is different, it will return that they are not equal, so you will be inserting it as a distinguished element into the set. But what is happening when we are comparing them? So what I wanted to get it is like this 2 1 is greater than 2 2. So basically when you are comparing, like we are coming from zip first, okay, it was equal, tax ID is equal, then we came to first name. Now when you try to compare first name, the first name is C for 2 1 and it is D for 2 2. And if you compare C and D, so C is less, right? That means TO1 is less than TO2. So if I write it as a less, it will return correct. Everything is correct, right? So it is comparing in that order. But what I wanted is I somehow I wrote this structure, let's say 5 years back, and now what I want to do is when I want to write my comparison, I don't want to compare in this order. Okay, I want to compare for zip. Once zip is compared, then I just want to directly go to last name, compare the last name. Now this is kind of library shared, and I can't change the layout, and other problems are there, right? So I have to write my own spaceship operator now. I can't rely on the default operator. Okay, so let's see. Now this is string type, and the string type is having the yesterday strong ordering, so I will just change it to strong ordering, and we'll write it for our own. And when I'm writing my own, okay, now what I will do, I want to first check the base. So if I want to check the base, what I will do is basically, let's say add to compare is equal to, or let me just copy paste the code instead of spending time there. So I will do something like this. Forget about other things, the other comparison, and let's say last what I want to do is a tax, right? So on any branch now I am returning a value, and here it should be that. Okay, but still you are getting a compilation error, right? Any idea why we are hitting this compilation error now? So this is beauty of the spaceship operator. So what it enforces you that when you are writing a spaceship operator, that function should be constant, because anyhow you are writing on the const type only, so it can't be other than const. So that's what was the missing, the const thing there. And now okay, everything is working fine here, right? And we are comparing tax side in it. So if you see, when I'm writing this comparison, what I am doing is the spaceship operator. Basically I'm not using less than, greater than, anything like that. What I am using is a spaceship operator defined for the other types. So let's say for example I have done for a base. Now after base, what I want to do, I want to compare for a last name. So what I can do is basically last name spaceship operator, and order doesn't matter here, right? That dot last name. And what I am saying is if the comparison is not equal to 0, that means it is not equal. If I found that it is not equal here only, why do I have to go further? I can just return from here only. See, and similarly, I will then write for, let's say, first name. Okay, and see, here only our program started passing, but for completion, just write it for first name. Okay, and let's say it is first name. Okay, this is perfect. See, and our program is also passing here. Now let's say, accidentally, see, strong ordering is like the strongest type. So let's say, for example, instead of strong ordering, if I wrote partial ordering, will it work? Yes. Why? Because strong ordering can be implicitly converted to partial ordering. Now let me just add another member variable here. Let's say double value. Okay, and let me compare that as well here and see what we have here. Okay, and here is, let's say, value, and here we have value. Definitely we'll get a compilation error because of this as well, because see, the aggregation whatever type we are saying is not correct there. It expects now 5 argument, we are passing one only. Now if I make it, okay, it is partial ordering, still fine, but if I revert back to strong ordering, now what will happen here is this will fail now. Why it is failing is because, see, here error is on line number 35. The category of this comparison, whatever is the return type here is, it is a partial ordering. Why? Because we saw the return type for the double or the floating points are partial orders. You can't convert the partial orders to strong order implicitly, so it will fail here. So this is a good sign for us that okay, we are not doing anything wrong. So this is the advantage of spaceship operator and enforcing this strong ordering, partial ordering, and weak ordering. So prior to C++20, there was no a standard way to enforce these different kinds of ordering mechanisms, and there was no standard rule. So everyone was, kind of writing their own classes, enums to have these different kind of comparisons available. Any question on this one? That how to write your own custom operators and what needs to be defined to make sure that your even the custom operator works. Okay, I'm moving further now. So if you see
Can
here,
you give
if
an
you try
example
to
of weak ordering also? Even if it is just a mention, it's okay.
example of weak ordering. So in weak ordering, basically, let's say what we can say in the weak ordering in a real-time example, string comparison is a weak ordering. String in case insensitive comparison, to be precise, right? Because what is happening there is we are not allowing incomparable value, uncomparable values. So okay, that so it can be strong ordering or weak ordering. Now when we are comparing and having it is like a case insensitive comparison, then the two strings can be different. Still, our operation will return it as like equal, but they are not actually equal. So we have to call it as equivalent. So in mathematical term, they are equivalent. So because they are still distinguishable values, right? We can see both the values and we can distinguish. Oh no, this is capital. Oh, this is small one. So in that case, it becomes a weak order.
Thank you. Thank you.
Okay. So now if you see the spaceship operator, one thing you can see from this code is when you are going forward, when you write these comparison operators, you will very hardly write the less than, greater than, less than equal to, greater than equal to, is equal to things. 90% of the time you will write only one operator, which is nothing but a spaceship operator. Even if you have to write it, I mean, if you are writing your class from this first time and you don't have any restriction on changing the layout, then you can have your semantics getting generated from the default operators itself. So in that case, you don't even have to write the code. So that's what spaceship operator for you. Now I will not go into the too much in depth of this overload resolution. Just copy pasted these rules from the cppreference.com. So if I have to say in a very simple word, so let's say for example you are doing some x less than y, right? Some comparison. Now what will come in picture in the resolution order? You will find, let's say, whether there is some member operator defined for that one. Then you will also find the non-member functions. And the third one in this case, you will find the spaceship operator. Now you will invoke that as well. And for not equal to as well, what you will do, you will try to find is equal to, because not equal to is not related to the spaceship operator. And for is equal to again the same thing. But then what is the tiebreaker here? So if you remember, the member variable is referred over the free functions, okay, that we know. So same rule applies here. But then let's say when you are doing x less than y and we have a member variable or free function defined x less than y, and then there is this spaceship operator, which one is picked? So the more explicit thing is always picked. So x less than y, whatever is that, if that is exist already, then it will be picked. If it doesn't exist, then it will have that spaceship operator with the same order, let's say x and y order, x spaceship operator y. If that is also not available, then it will look for the reverse order, which we call a synthesized one, that has a lowest priority for the order overload resolution for the operators. Okay, specifically for relational operator and this equality operator. So I mean, there were questions like on a Stack Overflow when you have, let's say, two classes, like base classes you are having, and in the base class you are having this less than operator as well, and then from another base class you are getting that spaceship operator as well. And so because you are having the multiple inheritance, then what will happen if you directly use less than? Then in that case you will hit an ambiguity, because both are kind of a different overload set and you don't know which one to pick. So in that case you might have to explicitly say that dot operator less than, instead of saying okay less than. So you can find such examples on Stack Overflow as well. Now coming to some utilities function, okay, we got a spaceship operator, that is still fine in that. But if you remember, we have this less than greater than operator, but along with that we have that stdle, stdgtle, right? The function object for performing a different type of comparison. So similarly, along with the spaceship operator, they have provided a function object for performing a three-way comparison, which is nothing but a std compared three-way. And you want to pass it, let's say, to your unordered map, or let's say set as a comparison function, or somewhere else as a template parameter, or anything else, you can use this std compare three-way. Now next time I think Ankur is going to take more on the template side. So in the template, the type deductions and that are kind of very hectic things, very error prone things and that. So let's say if we have two operators now, let's say two operands, let's say of type T and of type U, and then you want to find out what is the return type of when we apply the spaceship operator in unevaluated context. So in that case, we can use std compare three-way result, and which will tell you that okay, if you compare this, what type you will get, whether you will get a strong order, partial order, or will get a weak order. So this is what this type trait is for. Then there is another one which is called as a common comparison category. So what is a common comparison category? So let's say if you have some n number of different data types, and you want to compare them using the spaceship operator, and you want to find out what is the final type which you will get. So you can use this std common comparison category. This works very simply. So for example, if all the members whatever you have are, if they are all the strong type, then you will get basically a strong type. If any one of them is, let's say, a partial order type, you will get a partial ordering. Let's say any one of them is a weak ordering, then you will get a weak ordering. It's because this is how the order is. Yes, Ankur, you were saying something?
No, sorry.
Okay. So this is this STD common comparison category. So basically it gives the strongest comparison category which can be written by comparing all of these different data types. So this is what the point here. So we'll quickly go and we'll see STL simplification, and if time permits, we'll see the customization points. So I wanted to, okay, so I want to enable the link. So let me just, okay. I wanted every one of you to, look at this one. Now in this standard library, if you see how the spaceship operator, did a very well job and removed a lot of clutter from the standard library, especially due to comparison. For example, to check whether the objects refer to the same type, we had there is equal to and is not equal to as well, which is removed in C++20. Why? Because it can be generated from is equal to. For compare between two error codes, once again everything is removed. Is equal to is same, but the spaceship operator is introduced. You see a lot of places spaceship operator is introduced and almost everything is basically removed. You see here, right? You see there a lot of places, but there are still places where it's not done, and for every places it has different reasons. So I was trying to explore that why it is not let's say removed for other things. Okay, so for example, I was trying to find out why it's not removed for, let's say, a stack, why there are still other type of operators available with the stack. So let me search stack. Yeah, see here, if you see stack, you still have is equal to, not equal to, less than, and that all these are still available. I was just curiously looking into the implementation that, are they doing anything special with these operators, or I mean, what is the reason to keep it like that only? So the reason which I found for specifically for stack is that when you have a stack, there is a template parameter called as a container type, and you can provide that container type as a parameter. And whenever these operators are getting compared, basically what they are invoking the is equal to of the underlying container, or not equal to of underlying container, whatever the containers are there. Now you never know, right? It is coming as a template parameter. You never know for that whether the spaceship operator is defined or not. So you don't just want to rely on that and say or enforce that from today only, that whatever let's say container you pass for this stack as a template parameter, it should have the spaceship operator. So just to avoid this thing, they have kept this thing here. And for other, it might be similar. For example, to compare the time points, all right, again they might be having some different custom comparison between less than, greater than, getting some more performance. So I will say, this is a very good exercise to go and look into that, why blindly they haven't removed everything, all the other operators, and have kept it for some of the operators. This is a good exercise to understand how the STL developers think, and how if we remove it, for example, how it impacts the existing code and that one. Any question on this? Okay. So our time is already over, but I just wanted to touch upon this customization objects or customization points. I will not go into the deep of all these things. We'll just quickly cover into 2 minutes. So we have these 6 customization points. I am not going to explain what are these. So basically this strong order, if you pass 2 values, it will return strong order. By doing this comparison by using the spaceship operator. Again, for weak order, it is same thing, partial order, it will return a partial order. For compare strong order and fallback, what it will do? It will do the 3-way comparison if it is available and return the strong order type. If it is not available, 3-way comparison, then it does comparison based on less than, equal to, and greater than, and based on that result, it generates a strong order. Similarly, for weak ordering also, if the 3-way comparison operator is not available, it does fall back to less than, greater than, is equal to, does do the comparison and return the weak order. Similarly for partial order. Then why we need a customization points? I mean, there was nice talk by Inbal on customization points and that. So that's why I thought, okay, let me cover this point here. So basically, it's a very simple example. We'll take here for the customization points. So everyone knows this std swap. All right, this is one of the customization point. So how does it works? For example, if you define your own swap function for a particular namespace, then when let's say a particular algorithm is using in standard library using the swap functionality on your data type, by doing the ADL, what it does, it basically calls they swap your custom functions, right? And how do? They basically, wherever they are calling, they do like using std swap, and then they just freely use the swap function with unqualified name here. I mean, there is no namespace, nothing. And then first ADL kicks in, and then ADL sees that first and second parameter is of type color, which is nothing but in the namespace Maya, and it basically calls this swap. But the problem with this approach, the swap was designed like say 10, 15 or 20 years back. If I write std swap, so if you see here, the output is custom. So basically we are calling this guy. But if you write, let's say std swap here, then we don't get this swap will not get called. But with the customization point which is provided recently, even if you are std strong order, and now let's see if I define my own let's say strong, I have to define it into the namespace. So let me copy paste the code in the interest of time. It is exactly just writing the strong ordering function. Okay, so see, I am defining this function like a strong order. And if you see now, what is happening with the program is when I am calling this a strong order, so this void is written just to avoid that warning that you are not using the return value from the strong order. So if you see here, even if I'm calling the std strong order, still the call is landing here. So what will happen in this std strong order then? Then std strong order, it will do the concept checking to get more good errors there, and to exactly say, okay, why we are not able to call a strong order, what is the problem with the strong order. So when, let's say, when in the future it will evolve, it is not just only strong order, all customization point will be built around something like concepts and will give you good error warnings. And then now you can't do any mistake here, even though you are doing std strong order and you have a specialization in your namespace for that one, it still will call that customization point. And then here, if you want to do some custom thing, you are allowed to do that one. So that is what the customization point, which is again available for spaceship operators because it is introduced recently.